Check this out. We've got something really fun today. This is so amazing. Oh man, again? 9.1 antiderivatives. Let's take the derivative of these equations and look for a pattern. So the derivative of x squared plus 2 is just 2x plus 0 because the derivative of 2 is 0. To the derivative of this one, y prime is equal to 2x plus 0 again because the derivative of negative 2 is 0. And we do it again and we see that in every one of these cases we're getting the same derivative even though the original equation is different. So when we're doing antiderivatives, that means that we're given the derivative and we want to go backwards a step to the original equation. We can think backwards through our derivative rules that we've learned, and then we need to add an unknown constant. Because we don't know what constant was there, that information has been lost through taking the derivative. So we will do what the textbook does. We'll call f of x, capital F of x, to be the antiderivative of small f of x. Then the most general antiderivative of f of x is capital F of x plus c. Let's find the most general antiderivatives of these equations. So small f of x here is the derivative. We want to figure out what the original function was. So we've got to think backwards. What did we take the derivative of to get 4x cubed? We can look at the power rule. This one must have been x to the power of 4 before we reduced the power by 1 to get x to the power of 3. Now this also explains where the coefficient came from. We multiply the 4 in the front here, and that's where this 4 came from. And we reduce the exponent by 1, and that's where the 3 came from. So that's the antiderivative of the first term here. Let's move on to the second term. Now this one's x squared, so that means it used to be x cubed. We take the derivative, the 3 comes down in front, and we reduce the exponent by 1. Now the reducing the exponent by 1 makes sense because this is 2, but there's no 3 here. Where'd the 3 go? Well, we've got to account for that. So if I don't see a 3 here and I know a 3 is coming, I will divide by 3. That way that when the 3 drops down, and I got 3 divided by 3 is 1, and that's what I'm seeing here. Next one. This one used to be x squared. And I know that 2 would come down and multiply by something here to get 6. So that would have been a 3 right here. 2 times 3 gives me the 6. Reduce the exponent by 1 to get x to the power of 1. The next one is 3, so I know that used to be 3x before I took the derivative. And we need a plus c, and that c is a capital C. Let's take the antiderivative of the next one. Now the 4 is a constant, so I can just ignore that and work inside the brackets here. This x used to be x squared, and if the 2 came down in front, that would explain this 2 that we're seeing here. Plus, how did I get a 1? Well, a 1x would explain that. There. And plus c. Don't forget the plus c, or it would be wrong. If you like, you could rewrite this question and distribute in the 4 here. So 8x plus 4. And then do the antiderivative. We should end up with the same thing. So this is x, so it used to be x squared. And what was its coefficient? Knowing that 2 is going to come down, multiply by that to get 8, that would have been 4. This one here is just a 4, so that one used to be 4x. And then we need a plus c. And if we distribute in the 4, or if we don't, we still get the same antiderivative here, just written with brackets or without. Let's find the most general antiderivatives of these equations. So we'll say capital F of x here. Now what's the antiderivative of cos? Well, we know that used to be sine. So the derivative of sine is cos. And this negative wasn't created by the derivative, so it must have been there before. Let's do this one. The antiderivative of sine must have been cos. Now this one, the derivative of cos is negative sine, but we don't see a negative sign here, so it must have been canceled out. So put a negative here. That way it will be canceled out and just give us the plus we see here. And we need a plus c. The antiderivative of this equation would be, remember our exponent rules, e to the power of negative x. This derivative is e to the power of negative x times the derivative of negative x, which would be negative 1. Well, that would explain where the negative came from, but the 3 must have already been there because it's not created by taking the derivative. The next one here, same thing, I'm going to rewrite e to the power of 2x because I know that the derivative of that is still e to the power of 2x times the derivative of 2x, which is times by 2. So I'm going to multiply whatever was sitting here by 2 to get 6. So that means that there must have been a 3 here previous, and we need a plus c. Now the next one we have to look at very carefully. We've got 2 different terms here, but they contain the derivatives of portions of the other terms. So the derivative of the natural log of x is 1 over x. And the derivative of cos is negative sine. So this might have come from the product rule. So let's try that. We take the derivative of the first term, 1 over x. Well, that was probably this natural log of x. Then we multiply by, well, when we do the product rule, we leave the second term alone. So this would have been the second term here. When we take the derivative of cos, we get negative sine, leave the first term alone. So this one would be plus c. Now there's a pattern we should recognize, and that is if you have x cubed, the derivative is 3x squared, right? And if you have x squared, the derivative is 2x to the power of 1, say. And this one is, if you just have x, then its derivative is just 1. And you could write like x to the power of 0, you know? And then if you had x to the power of 0, see, we're trying to make this pattern 3, 2, 1, 0. And what's the derivative of x to the power of 0? Well, x to the power of 0 is actually equal to 1, so its derivative is 0. Then we go on. What's next in our line here is x to the power of negative 1. And the derivative of that is negative 1, x to the power of negative 2, or negative 1 over x squared. You notice the thing that's missing here? Yeah, it is 1 over x. And so if you ever get a 1 over x, stop looking for the power rule to give you that and look for the natural log. If we had a function like this, we might want to rewrite just this part here. And so then we can use the power rule more easily. So 2x to the power of negative 2. This one I won't rewrite because I see that it's a 1 over x, and I know that the natural log of x created that. So I'll just leave that one there, and plus x. So the most general antiderivative here would be, let's look at the first term. We had a negative 2. So before it was negative 2, it was obviously negative 1 before we reduced it by 1. And the negative 1 dropped down. Now I don't see any negative here, so I must need a negative to cancel it out. I also have a 2 here, which isn't created by the derivative, so it must have been there before. You can always double check by taking the derivative of this and make sure you get this. Minus. The 5 is just a constant, so I'm going to leave it there. And I already said before, 1 over x, the antiderivative of that is the natural log of x. And the antiderivative of x is x squared. And the 2 would come down if I took the derivative. I don't see a 2, So I need to divide by 2 so that that 2 will cancel and not show up here. And of course I need a plus c. Now this one here, I'll just rewrite this. Sine x plus x to the power of negative 3. And we'll do the antiderivative. And the antiderivative of sine would be negative cos. Because the derivative of cos is negative sine, but I don't see a negative there, so I need to put one here to cancel out the one that will come from the derivative. Next, you do the same thing for this negative sign. I know that the negative would come down here and make this positive, so this must have been negative. And before I subtracted 1, it must have been x to the negative 2. Okay, so I see my negatives will cancel, give me this positive. And the 2 is going to come down though, and I don't see a 2. So I need to divide by 2 so that when the 2 comes down, when I take the derivative, that 2 cancels and I don't see it here. And I need a plus c. Now this one's a real stumper, but pretty fun. If we look at this, it's just one term. So how did that happen? Well, it wouldn't happen with the sum or difference or product rule. We would see probably another term here being added. So one of these things probably came out of a chain rule. So if we just look at this, our antiderivative could have been something like sine squared x. And the 2 would drop down in front. I don't see a 2, so we'll have to divide by 2 here. The 2 would drop down, cancel with this 2, and just leave us with the sine. Now the derivative of sine, remember the chain rule, is cos, and that would explain cos's presence here. And so then plus c. But that's not the only thing that could have happened here. If we consider cos being our primary function, could have been f of x is equal to, how about cos squared? And the same thing could have happened with that to produce this. Now we do have a negative. When we take the derivative of cos, we'd get negative sign. I don't see a negative, so I just need to add that in there. And last one is using some identities. So if I looked at this, this is actually kind of like if it just had a 2 in front, like sine's double angle identity. I can just randomly add a 2 in front, but I can multiply and divide by 2. Okay, so I'll just erase that and rewrite it here. So 2 sine x cos x divided by 2. This is sine's double angle sine 2x over 2. And now, what would be the antiderivative of sine 2x? Well, let's see. It used to be cos, and I don't need any squared this time because the derivative of cos is negative sine. I don't see a negative, so I'll have to add that in there. And it was a 2x. Now, when I take there's also a divided by 2. When I take the derivative of the inside here, I'm going to get another 2. So that will show up. That would have shown up here. I don't see a 2. In fact, I see it divided by 2. So that means that I need to divide by 4 to cancel out the 2 that's coming out of this function here and leaving me with a 2. And plus c for that one as well. And you can see that these are pretty different. And if we let our c value equal 0 and graph it, then this is what it looks like here. You can see why this is happening. The derivative at every x value is the same. It's just these graphs are in different places, but the derivative doesn't recognize what height we're at. It's just looking at the slope of the graph. And so you can see that each one of these are very different, but the slopes at every point are always the same. You should be able to find the most general antiderivative. Here's some questions from the textbook. Give them a try. See if you know what you're doing.